We are back with another Further Maths A-Level tutorial, and today, I'm not going to lie, it's a pretty cool topic because we are looking at roots of a complex number, sometimes known as nth roots of a complex number. And this is a pretty cool topic because it's one that's often chosen by people making videos as a topic that's quite easy to blow people's minds with. But we're just today going to just casually do it because, you know, we're doing Further Maths A-Level. This is just a walk in the park, a daily occurrence for us. But anyway, more specifically, what this topic is looking at is solutions to equations of the form z to the power of n equals k, where n is a natural number, or in other words, n is a positive integer, and k is any complex number you like. A reminder, of course, complex numbers is the 7 numbers that involve all the real numbers, involves all the imaginary numbers, and all the numbers that involve the combinations of those two things, which is what a complex number is. And also, it's worth pointing out, before we actually launch into solving it, we kind of already know what we're expecting to find. Because when we were looking at complex numbers earlier in the complex numbers chapter, as part of the AS content, you will have noticed that when we're solving polynomials, things like quartics, cubics, and stuff like that, the number of solutions you got was always the same as the power, or the order, I should say, of the polynomial. And that meant, okay, sometimes you could have repeated roots, so you wouldn't necessarily get that many different solutions, but you would, for instance, if you have a quartic, highest power is 4, so you got 4 roots. So therefore, for our equations we're looking at, as we've got a power of n, we know we're expecting n roots as the solutions to this equation. Nice. So, how do you go about finding the first root? Because we'll deal with that bit, and then we'll deal with finding all the other roots after that. But to find the first root, my first bit of advice would be to look at the complex number you have already in the equation and to convert it to exponential form. Now, admittedly, you could actually convert it to, or leave it as modulus argument form instead if you wanted to, but you must remember that modulus argument form and exponential form are telling you the exact same bits of information, but exponential form does it with you having to write less stuff. So from a laziness point of view, it's nicer to write in exponential form. No mathematical reason though why you'd do that over modulus argument form. And then once you've done that, it's actually really easy to find the first root. All you got to do is use the power of 1 over n to combat or undo the power of n that you already have. So for instance, if your equation is z squared equals a complex number, use the power of a half. If you've got an equation that's of the form z to the power of 9 equals a complex number, use the power of 1/9 to find that first root. Then let's look at an example. So we could look at the example z to the power of 5 equals minus 512 root 3 plus 512i. And so therefore the first thing we're going to do is we are going to convert that number to exponential form. So starting off with the modulus, because that's the easy bit. I say easy bit, admittedly, worth pointing out that we are dealing with some very big numbers here. So you're going to want to use a calculator because nobody wants to do 512 root 3 all squared in their head. And if you type that into calculate, you get 1024. So that's the modulus of our complex number. Then find the argument. Call back to one of my other videos. Good bit of advice. Draw an argument diagram so you get an idea of what sort of argument you're trying to calculate. We got a negative real part, a positive imaginary part. So it means we know we're in this top left-hand quadrant, and therefore the argument is the angle that I've just indicated there. But to find it, probably easier if you have the right angle triangle over here. It's a right angle triangle with a base of 512 root 3, a height of 512. So we can very easily find this little angle here by using arctan. You notice I'm not including the minus signs inside the arctan here. I'm just treating those numbers as the lengths of the sides of the triangle. It's much easier that way. Opposite over adjacent would get you that. But then we realize that's not actually the argument yet. That's just that little angle inside the triangle, and the argument is that other angle outside the triangle. And we realize these two angles together lie on a straight line, so pi minus the angle inside the triangle would get the argument, the angle that we want. So if you do that calculation, you will get 5 pi over 6 radians. arguments always being in radians, a little reminder. So therefore we can now rewrite our equation because it's now z to the 5 equals, and our complex number has been rewritten, or can be rewritten, I should say, as 1024, the modulus, lots of e to the power of the argument times I. So that would be 5 pi over 6i in this case. And then we can find the first root because all we got to do is use the power of 1/5. So therefore z to the power of 5 to the power of 1/5 is just z. That's the whole point. We'll find the first solution to this equation already. And then we're going to do 1024 e to the power of 5 pi over 6i, all to the power of 1/5. And it's at this point you probably start to see why I like to write the complex number in exponential form. It's because at this stage, then it just means you're applying index laws to find that first root. Because we can, by index laws, apply the power of 1/5 to the individual factors here. The 1024 can be taken to the power of 1/5, and then the e to the power of 5 pi over 6 I can also be taken to the power of 1/5 as well, individually. Now, conveniently, 1024 to the power of 1/5 is just 4. How lovely. And e to the power of 5 pi over 6 I to the power of 1/5, that looks a bit crazy, but by index laws, all you've got to do is multiply the powers together, and that means you just get 4e to the power of 1/6, or pi over 6, depending on how you want to write it, lots of I in a power. So 4e to the pi over 6i. There you go. That is our first root done. It's genuinely as easy as that, always. But what about the other roots? Well, this is where it gets really interesting because we decided before to write our complex number as z to the 5 equals 1024 e to the power of 5 pi over 6, lots of I, which is correct. But when you look at an Argand diagram, you very quickly start to realize that there's more than one way you can write the argument of a complex number. Because normally we do the sensible thing of just taking the argument to be the angle directly between the positive real axis all the way around until you get to where your complex number is. But why do we have to stop there? We could continue around with measuring our angle, keep going on, keep going around, all the way until we get back to the complex number again, but in doing so having travelled an extra 2 pi radians all the way around the Argand diagram. So, therefore, that would be the same complex number, even though it looks like a different complex number because it'll have a much bigger argument. So if we do that to our complex number, we'd have z to the power of 5 equals 1024 e to the power of 5 pi over 6 plus 2 pi, lots of I. And if you simplify that, you'll realize we have 1024 e to the power of 17 pi over 6, lots of I. Now the reason that's intriguing is because, as I already said, that looks like a different complex number even though it is actually secretly the same complex number. But then things get weird when you decide to then find what z is. Because we could then choose to use the same tactic we had before of using the power of 1/5 to find what z is equal. But therefore we have to apply the power of 1/5, I should say, to our new complex number. And if we do that, the thing is we end up with a different answer to what we had before. The 1024 to the power of 1/5, that bit still does become 4, so we still have the modulus of 4 as our solution, but then the argument ends up being completely different. We end up with 17 pi over 6 to the power of 1/5 becoming 17 pi over 30 I in the power. But this time, with this complex number, that argument not only looks different to the argument of the solution we had before, it is a completely different argument visually as well. It's a completely different position on the Argand diagram. So, therefore, we've got another different solution, a second solution. And we can find a third solution by repeating that process again. And all you'd have to do is add on another 2 pi onto the argument, or add on 4 pi onto the original argument, however you want to view it. And if you were doing that, you would end up with 1024 e to the power of 29 pi over 6, I. And then we could take the power of 1/5 of that, and then we'd end up with something different. Because we'd end up with 4e to the power of 29 over 30 pi I. And again, that is an argument that not only looks different, it is a different argument. It is a different position on the Argand diagram. So that's interesting because it means we can then just continue this process on until we've found all the solutions we want. We're expecting 5 solutions, so you'd have to do this another 2 times. However, there is a quicker way, because although we now do have a method for finding all of the roots of our equation that we're looking at, there is a lot of unnecessary inefficiency introduced by repeating certain steps that don't really need to be repeated just because of the way we're approaching it. The thing is, if you look at what we were doing, we are each time having to go back to the complex number that was in the original equation and add 2 pi onto its argument, then take the nth root of that new complex number. And that would just find one extra root. And if we want to find another extra root, which we often will until we've found all the roots we need, basically, we're then having to go back again and again add a different multiple of 2 pi on and again take the nth root again. And so therefore that is a lot slower to do than what we could do instead. To find out what we could do instead, well, let's take a look at that process we were just talking about. We were talking about having an argument of a complex number, adding 2 pi onto it, and then if it's the argument placed as part of a power in a complex number in exponential form, what we're doing is then taking the nth root, which then applies a factor of 1 over n to that argument. But we can have a look at that fraction that appears as the power and realize that we can split that fraction up, that argument as well. Because we can split this fraction up as theta over n plus 2 pi over n. And that means we can save a bit of time because we know ultimately we could just start by taking the original complex number and taking the nth root like normal that we usually do to find the first root of the equation, and that is conveniently just this bit here. All we then have to do to that first root to find all the other roots is then add on multiples of 2 pi over n onto the argument, because therefore we can see that the nth root taken after adding an argument of 2 pi onto something is the same as just adding straight away 2 pi over n in the first place. So that is the much quicker way of doing it. And it is also worth pointing out that therefore we could point out that the modulus of the complex number is all the same as each other. There is another way, though, you could look at this sort of stuff to help you remember why we are just allowed to add 2 pi over n radians onto the argument each time to find the other roots, and that is to look at what's going on geometrically. If you were to plot all the roots to an equation of the form z to the n equals k with the same restrictions we were talking about earlier, you will notice that if, for instance, we're solving an equation that was z to the power of 6 equals, I don't know, let's say 4, the roots would end up being spaced, or distributed I should say, evenly about 2 pi radians. So that means the argument as a gap between each complex number that is a root to the equation ends up being the same each time. And in fact, even more than that, because we already know we're expecting n roots, therefore, if there's going to be n roots in this case, for this little example here, there would be 6 roots. The amount of a gap in terms of argument between each root would be 2 pi divided by the number of roots. So therefore 2 pi over 6 in this case, or pi over 3. So visually, that's also why we're allowed to just add 2 pi over n onto the argument to get the next root, because of what's going on geometrically, because they're spaced evenly about 2 pi radians going around. So let's put this all together in one big example. Let's say you've got a question like this. Also, while doing this also gives me a good opportunity to bring up some other little key details at the end. Anyway, splitting the page down the middle, roughly, so I've got more room to work in. First thing you want to do, rewrite your complex number in exponential form. Now, I'm saying complex number partly because this is one of the sort of questions that sometimes fools people because they see this number and go, that's not a complex number, there's no I involved. Well, no, it is a complex number because even real numbers technically are in the set of complex numbers. So therefore we have z to the 7 equals minus 1 over 2187, and therefore we can write that as a number in complex exponential form because we realize that will be a complex number with a modulus of 1 over 2187. That's a positive number, I'm not making a mistake there, because if we draw an Argand diagram, any number that's on the negative real axis is a number with an argument of pi. So therefore, our complex number would be 1 over 2187 e to the pi I. That means we can find our first root by just taking the power of 1/7 of 1 over 2187 e to the pi I, which is actually very easy to do because you've got to do 1 over 2187 to the power of 1/7, which you can type into the calculator, and e to the power of pi I to the power of 1/7, and therefore that very quite simply gets you 1/3, because that's what 1 over 2187 to the power of 1/7 is, and you get e to the power of pi over 7 I. There you go. So that is our first root done. How are we going to find the others? Well, all the others are going to be spread or distributed evenly across 2 pi radians. So that means there's going to be a gap of 2 pi divided by n, and for us our n is 7. So therefore, the gap between each root in terms of arguments is going to be 2 pi over 7. So therefore, for our other roots, all we have to do is add 2 pi over 7 onto the arguments. So therefore, we'd get z equals e to the power of 1/3, because they're going to have the same modulus, just a different argument, e to the power of 1/3 e to the power of 1/7 pi plus 2 pi over 7. So therefore that will get you 1/3 e to the power of 3 pi over 7. And we just got to continue that process on. And therefore we're just going to keep on adding 2 pi over 7 onto the argument each time. So we also get 5 pi over 7i. We also get 1/3 e to the 7 pi over 7i, which is a silly answer, and I will talk more about that later, but obviously it's pi I. Or 1/3 e to the 9 pi over 7i. 1/3 e to the 11 pi over 7i. How many roots have we got so far? 1, 2, 3, 4, 5, 6. One more to find. 1/3 e to the 13 pi over 7i. I know that's the last one because now I've got 7 roots. And a reminder, you're always expecting the number of roots to match the number that is in your power. So we've got our 7 roots. Cool, we've solved the equation. However, one little extra detail I want to draw to your attention is that it's always important in these questions you pay attention to how they want you to leave your final answer. They can ask for the complex number answers to be written in any of the 3 formats we have for complex numbers. That can be back in Cartesian, a plus b, I form. It could be in the modulus argument form, which is what we got here. Or they can say, fine, leave them in the exponential form if they're feeling kind. However, if they're asking for it in modulus argument form or exponential form, you do also have to pay attention to make sure you're leaving your argument in the format they want. So you'll notice they want the argument between pi and minus pi. So that's important because it means that some of our roots, like 1/3 pi over 7i, 5 pi over 7i, and, pi I, once you've simplified the 7 over 7 part, are all already complex numbers with the correct argument, which need to write them in the correct form. But then these complex numbers at the bottom, we are then going to need to rewrite their argument as well, not just their format. So therefore, the answers are going to be z equals, we'll have 1/3 cos of pi over 7 plus I sine pi over 7. We will have 1/3 cos of 3 pi over 7 plus I sine 3 pi over 7. So these initial ones, it is just me rewriting the format, not really changing much in terms of calculations. We're also going to have 1/3 cos of 5 pi over 7 plus I sine 5 pi over 7. The next number is an interesting one. Again, I've already pointed out that that is just an argument of pi. But there is an added extra element to this, which is that actually a reminder back to the beginning where we pointed out that an argument of pi I is technically just a negative real number. So it would be very tempting to simplify this complex number to actually being just minus 1/3, because that is what 1/3 e to the pi I would be. However, because they've asked it in modulus argument form, I would be tempted to still leave it with the cos and the angle, the argument, and all that sort of stuff. So, yeah, worth bearing that in mind. If in doubt, write both. But my natural instinct would be to say they probably want you to write it in that format there, even though it is just minus 1/3. And then the others, well, how are you going to rewrite them? Because the argument is too big. Well, once again, reminder, you can add 2 pi onto the argument of a complex number, and it's still secretly the same complex number. But you can also take away 2 pi from the argument of any complex number, and it's still the same complex number. So all you got to do is take away 2 pi from the arguments of these 3 complex numbers here, here, and here, and that will lead you to the last 3 solutions. So taking away the 2 pi from 9 pi over 7 will get us to 1/3 cos of minus 5 pi over 7 plus I sine minus pi over 7. We'll also get a 1/3 cos of, if we take our 2 pi off 11 pi over 7, we will get our minus 3 pi over 7 plus I sine minus 3 pi over 7. And then one more to do. All we've got to do is take away 2 pi from 13 pi over 7, and you get the last one, which is 1/3 cos of minus pi over 7 plus I sine of minus pi over 7. And there you go, 7 roots. Always worth checking and counting how many roots you've got at the end to make sure you do have them all and you haven't missed any out. But those are the solutions to the equation, and we are done. Those are all the steps you need to do in order to be able to find the roots of a complex number. So those set steps every single time, something you can very much practice. Although this is very, crazy maths, it is very much stuff you can still just practice and just get used to doing. There you go. Hopefully you found today's video useful. I will see you in a future video. Goodbye.